this is section 9.3, and this covers the integral test and the P-series test. So if we look at our formula sheet, so far we've talked about the telescoping, the geometric, and the nth term tests. So here we're going to be just working our way down the list. We're going to talk about the integral test, the P-series test, and I'm going to go ahead and just throw in the logarithmic P-series while I'm here. This is just kind of another one that's a very special case, but when they do show up, it's a lot easier to just recognize them rather than just trying to use the integral test. So we're really going to do all three of these. I just decided to throw this one in as well. Okay, so in this section and the next few, we're going to look at series that have non-negative terms. So what do I mean by non-negative? You might think, well, not negative must mean positive. Yes, positive or zero. The reason for this is because non-negative series, so positive or zero term series, have partial sums that form a non-decreasing sequence. Remember, non-decreasing is increasing or constant. And in section 9.1, we said, hey, a non-decreasing sequence that's bounded above is going to converge. So the integral test is going to give us a bounded above kind of a thing. So basically a series of non-negative terms, that's positive or zero, is going to converge if its partial sums are bounded above. Now remember from Calc 1, the integral of a non-negative function is the area between the function and the x-axis. So what we're going to do is combine that fact with the stuff from 9.1 and we get the integral test. So let's say that a sub n is a sequence of positive terms, and each one of these a sub n's in the sequence is equal to the function value at n. The function would have more in-between values, so it'd be nice and continuous and stuff. The sequence itself would be sort of smaller than the function. Now, f, the function, is going to need to be continuous, positive, and decreasing in order for this all to work. Okay? And it's going to need to be this positive, continuous decreasing function of x for all x greater than or equal to n, where this n is going to be this lower bound of our improper integral. Okay? What this is going to tell us is that the series and the integral are going to do the same thing. If one converges, the other converges. If one diverges, the other diverges. Now, looking at our formula sheet, here's how we're going to read this off. So we look at the integral test on the formula sheet, and you'll see, and it's a little blurry here, but it says f is continuous, positive, and decreasing. That's the first thing you need to ask yourself. Is the function continuous, positive, decreasing? If no, if not all three of these are met, then you can't apply the integral test. Move on to another test. If yes, then we're going to evaluate this improper integral. Once we've evaluated this integral, if it converges, so does the series. If it diverges, so does the series. So it's rather than trying to draw a picture and show you how that's going to work, I think it's easier to just dive right into an example and then kind of show you with that example. So let's go to example 1. Does this series, 1 over n squared, converge or diverge? Okay, well, remember how I said that the nth term test is like your go-to test? You really should try it first before you try anything else. So I just want to show you that the nth term test is not going to work here. It's inconclusive. All right, so let's just go ahead and apply it. So for the nth term test, we would take the limit as n goes to infinity of 1 over n squared. All right, so we get 1 over something getting infinitely large. That's going to go to 0. All right, so the nth term test is inconclusive because the nth term test says, hey, if that's not 0, you're done. You diverge. Move on. If it is 0, the nth term test is inconclusive. All right. All right, let's look at the corresponding function. All right, so let's look at the function f of x is 1 over x squared. This function is going to have the same values as this series does. When I plug in 1, 2, 3, the function is going to have those same values and more because, because we get those in between values here. Now what we need to know is this function positive, continuous, and decreasing. It doesn't need to be everywhere, it just needs to be everywhere bigger than 1. Just because this is indexed from 1 to infinity. All right, so is it positive, continuous, decreasing? Well, what does the graph of this look like? So, maybe if you don't know what this graph looks like, you break out a calculator and maybe just sketch a quick graph of it. So it looks like that. So everywhere from 1 to infinity, this graph is above the x-axis, so it's positive. It is continuous. The only discontinuity is at 0. Doesn't matter. I only need it to be continuous on this interval. And is it decreasing? Yeah. Look, as x's are getting bigger, the y's are getting smaller. So yes, those conditions are met. All right, that means that I'm going to evaluate this improper integral, and whatever it does, that's going to tell me what my series is going to do. All right, so I'm going to evaluate the improper integral from 1 to infinity because that's what my index was up here. So it's from 1 to infinity of 1 over x squared dx. That's not a terrible integral, right? I'm just going to use the power rule. It's going to be from 1 to infinity. I'm going to bring that up, make that x to the negative 2 dx. All right, so if I integrate that, that's going to be x to the negative 1 over negative 1. Okay, so I get x to the negative 1 over negative 1. That can be simplified a little bit, and I can just write that as negative 1 over x. I'm also going to go ahead and replace that infinity. Remember back when we did these improper integrals? So I'm going to go ahead and write the limit as b goes to infinity of negative 1 over x from 1 to b. So I did two things right here. I rewrote this a little nicer. I wrote it as negative 1 over x. So I just rewrote that nicer. And I went ahead and brought in that b up here. You can call it a, it really doesn't matter, whatever you want to call it. because that's where my limit's going to come in for that improper integral. All right, so let's take this limit. So the limit, b goes to infinity. Or actually, sorry, I'm not going to take the limit just yet. I do need to plug those in before I take that limit. So that'll be negative 1 over b minus negative 1 over 1. Now I'm going to take the limit. Okay, so b is going to infinity, so I get negative 1 over something getting bigger and bigger and bigger. That's approaching 0. So this is approaching 0 plus 1, which is 1, a finite number. The integral converges. If it diverged, this would be infinite or negative infinity. All right, that means the series of n from 1 to infinity, my original series, also converges. Okay, so I started off with this series. Just as a side note, I'm like, hey, look, the nth term test is inconclusive. Just wanted to show you that real quick. Okay. In order to use the integral test, we need to ask ourselves, is this function, notice it's just the function version of this, is it positive, continuous, decreasing? We graphed it and said, yes, it is above the x-axis, it's decreasing, it's continuous everywhere on this particular interval. Of course it's discontinuous at 0, but I didn't care about that. I only care about this 1 to infinity interval. So this was just the graph of it. You can use your calculator to get that if you need. All right, now let's just look at a picture. How are the integral and the series related? Well, remember that the integral is going to be the area under the curve. The series here is not quite going to be that full area, right? So this series, if I expand it out, I get 1 plus a fourth plus a ninth plus a 16th. Remember these Riemann sums that we did back in Calc 1? Those rectangles, the area of those shaded rectangles are these terms of my series. So when I start talking about the cumulative area, now I'm starting to talk about the partial sums of my series. So the area under this curve, here's where it gets a little weird, because the area goes from 1 to infinity. So we get this extra little box over here, and that's what's going to change things for us. If the area under this curve from 1 to infinity converges, that means the area is finite. So if I take that finite area under the curve, then of course this stuff, which is smaller, must also be finite. And then I add to it this finite box right here. Okay, I'm finite, I converge. The diverging is a little weird, because if this were to diverge, you might say, well, this is smaller, and it is. But it turns out that these boxes, when you shade them in, plus this, happens to be bigger than that total area from 1 to infinity under the curve. So if that integral diverges, then this is going to diverge as well. So anyway, I just kind of wanted to just kind of show you how these two are connected, just kind of quickly. All right, let's move on to another integral test problem. So does this converge or diverge? Well, let's use the integral test. So the first thing we need to ask ourselves is about the function. Okay, so let's look at this function. So does f of x being 1 over x times ln x, you know, I said does, I should have said is. It's gonna bug me. I was gonna say does it meet the criteria, but then I'm like, oh no, I don't like how that sounds. So, and because I'm not picky patty about this stuff. All right. Is this function positive, continuous, and decreasing for x greater than or equal to 2? Why do you think 2? 2's a weird index to start with. Why 2? Well, that's because the natural log of 1 is 0, and so it would get 1 over 0. So that's why. Okay, so we bust out the calculator. I knew what 1 over x squared was going to look like. So let's get a graph of what this is going to look like. So 1 over x times the natural log of x. Let's see what it looks like. Alright, let me zoom in a little bit. So we got little action going on over here. Doesn't matter, we're only interested in 2 to infinity. So 2 being right here, look at what's happening after 2. Let me go ahead and zoom back out. So you can see that we've got this decrease kind of business going on. It's above the x-axis, so it is positive. And it's continuous. The only point of discontinuity here, well, there's 2 of them, 0 and 1. But neither of those are part of our interval of interest. So it is going to be positive, it is going to be continuous, it is decreasing. So yes, we can use the integral test. Alright, so we need to integrate this. So we're going to integrate from 2 to infinity, 1 over x times ln x dx. Alright, how are we going to integrate that? Why is that blurry over there on the edges? Alright, how are we going to integrate it? Well, we're going to have to use a substitution. So let's let u be the natural log of x, because the derivative of the natural log is going to be this 1 over x dx. So making that substitution, I'm going to get 1 over u, and then this 1 over x dx is going to all get absorbed into my du. Oh, this is going to be weird. Because look, when I integrate that, the integral of 1 over u is natural log of absolute value of u. But u itself was an absolute, or was a natural log, so this is going to be weird. Yeah, I got the natural log of the absolute value of the natural log. Crazy, huh? And that's going to go from 2 to infinity. Alright, let me just throw that limit in here. So the limit is b goes to infinity of ln of absolute value ln x from 2 to b. That's going to be the limit as b goes to infinity. Alright, so if I plug in b, that'll be the natural log of the absolute value of the natural log of b minus the natural log of the absolute value of the natural log of 2. Ooh, that looks a lot like a 21 there, doesn't it? Okay, let me fix that. Ooh, Okay, so what is all this doing? Well, as b goes to infinity, the natural log function, so just in case you don't know what the natural log function looks like, it looks like that. It is an increasing function. As this number gets bigger and bigger, the natural log gets bigger and bigger. So this inner stuff right here is going to infinity as this goes to infinity. If this argument's going to infinity, the natural log of infinity is going to infinity. All right, so that means that this integral diverges. All right. And we can go ahead and say, so the integral and the series both diverge. And something kind of cool about this one, this sucker diverges so slowly. I mean, so slowly. If we're like, yeah, it's going to add up to infinity, it's going to take a long time. Like, the sum of the first 10,000 terms is only like 3. It is such a slow diverging sequence, or series here. Okay, so this one, so we saw how to do this using the integral test, but check it out. This sucker is a very specific case of a logarithmic p-series. That's the ones that have 1 over n times ln n to the p power. And look, they always start their indexing at 2 because remember the natural log of 1 is 0. I'm not going to divide by 0. So this one is specifically a logarithmic p-series. If p is that power outside of that natural log, that's a logarithmic p-series where p is 1. A logarithmic p-series where p is equal to 1 diverges. So this is a logarithmic p-series where p is specifically 1, so it diverges. If this were to show up on, a test or a quiz, you absolutely can use the fact that this is a logarithmic p-series and go straight to this test and say, boom, it diverges. I just wanted to show you with the integral test how this would shake out. So, and okay, so how did I know that p was 1? That's because this was n equals 2 to infinity of 1 over n times ln n. So that, if I want to match it up with that p-series type here, that would be the natural log of n to the first power. So because there's no exponent on there, we know it's to the first power. So that's why we would that p would be 1 for that logarithmic p-series. All right, so yeah, just wanted to show you that that was a very specific case. And if you didn't catch that it was a very specific case, that is okay, because you could have just used the integral test on it as well. Okay, so let's look at the next one here. Does this converge or diverge? Much like the 1 over n squared, its limit is going to go to 0, so the nth term test is going to be inconclusive. So let's look at the function of 1 over x cubed. Is this function positive, continuous, and decreasing? Doesn't have to be that everywhere, just from 1 on. We'll see what 1 over x cubed looks like. So if you don't know off the top of your head, that's okay. So let's get a graph of 1 over x cubed. All right, let's zoom in a little bit here. Ooh, so it's kind of going down and over here. For all the x values of 1 on, it is decreasing. It is above the x-axis, so it's positive, and it's continuous. In fact, we can look at this and say, hey, it's continuous everywhere except 0. But that's okay, because I'm only interested in 1 on. So yes, it is. So I'm going to say yes. And then I'm just going to put a little side note that we're looking at the graph. On the calculator. That way if you look back at these later and you're like, she says yes, how did we know this? But did it come to me in a vision from a burning bush or something? No, it was on the calculator. All right, so let's integrate. So let's integrate from 1 to infinity. 1 over x cubed dx. So if I rewrite this as x to the negative 3, then this is just a power rule that I can integrate. That'll be x to the negative 2 over negative 2. So x to the negative 2 over negative 2, and that's going to be evaluated from 1 to infinity. Just like I did last time, I'm going to clean that up. So let's do the limit as b goes to infinity. I'm going to move that x to the negative 2 to the bottom. So let's make this a little nicer and make it 1 over negative 1 over 2x squared from 1 to b. Alright, so let's plug in b and 1, subtract, and then evaluate that limit. So that limit as b goes to infinity of negative 1 over 2b squared minus negative 1 over 2 times 1 squared. Alright, so as b goes to infinity, we've got negative 1 over something getting big, 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 big. So we know that 1 over big is 0, so it's negative 1 over big. So that's going to go to 0. Alright, so that's going to be a positive 1 over 2 times 1, or just positive 1/2. That is a finite number, which means it converges. It being the integral. By the integral test, that tells me that the series must also converge. Right? So, because this is finite, the integral converges. Alright, so therefore, the series also converges by the integral test. Okay, let's go on to this next one. 1 over n. Alright, by now you kind of probably have a good feeling for what's happening here. Right? let's just look at, you know, is this function of 1 over x positive, continuous, and decreasing everywhere bigger than 1? Decreasing. For all x bigger than or equal to 1. Well, do you guys know what the graph of this one looks like? This is one that you've probably seen before. 1 over x looks like that. It is discontinuous at 0. That's cool. We don't care. It just has to be continuous everywhere bigger than 1 and equal to 1. So everywhere bigger than or equal to 1, yes it is, above the x-axis, so it's positive, it's continuous, and it's decreasing. See, it's going down. Those y values are going down as the x values are getting bigger. So yes. So we apply the integral test. All right, that means that we are going to integrate from 1 to infinity, because those are my bounds there for my index, of 1 over x dx. That's a nice integral, right? That's just natural log of absolute value of x from 1 to infinity. Let's bring in the limit. As b goes to infinity, ln absolute value of x from 1 to b. So that's the limit as b goes to infinity of the natural log of the absolute value of b minus the natural log of the absolute value of 1. As b gets bigger and bigger, the natural log of b also gets bigger. So that's going to infinity. That means that this is going to diverge. This improper integral is going to be infinite. So we can say that that's going to be infinite. So therefore, the integral and the series both diverge. Now, this is the second time we've encountered this one. So remember when I said you can always use the graph. As x gets bigger and bigger, the y value gets bigger and bigger for the natural log function. So this is the graph that's in my head when I'm saying that, hey, this is going to infinity. That as these x values are increasing, the y values are also increasing without bound. Now, this one actually has a name. Believe it or not, it's actually popular enough that it has a name. This series from 1 to infinity of 1 over n is called the harmonic series. Has a lot of pretty cool applications to physics. But yeah, it's actually just popular enough that it gets a name. Okay, so here's where we're at. Specifically, series of this form. So you can see that, we kind of keep coming back to these, like 1 over n squared, 1 over n, 1 over n cubed, things like that. And those are called p-series. So we have that on here. So a p-series is 1 over n to the p power. When p is greater than 1, the series converges. When p is less than or equal to 1, the series diverges. All right, so is a p-series where p is 1. So if it's equal to 1, it's going to diverge. P-series, p equals 1, the series diverges. Back in example 3, we had n cubed. That's a p-series where p is 3. So it's bigger than 1. It should have converged, and it did. The very first example that we did was 1 over n squared. That's a p-series where p is equal to 2. That's bigger than 1, so it should have converged. And it did. So, yeah, I figured I would go back and point all that stuff out. So, while these p-series may look like super easy, and you may think, oh, these aren't going to show up very often because they're almost too easy, they really are going to show up a lot because they're really useful in the next section when we have to do comparisons. Because they are easy, they're an easy comparison to make. Okay, so let's look at this one. This was a p-series. It may not look like a p-series, but it is. That's because, remember, that square root of n can be rewritten as a 1/2 power. So if I rewrite this as n goes from 1 to infinity of 3 over n to the 1/2, okay, now you can see that's a p-series. Now you may be like, oh, okay, well, does that 3 throw things off? No, not at all. Because it's just a constant multiple, you can pull it out of the series. And the constant multiple doesn't change the convergence or divergence. If this converges, multiplying by 3 is not going to change that it's finite. And if it's infinite, multiplying by 3 is still going to keep it infinite. So this is a p-series. Where p is 1/2. That's bigger than 1. That's less than or equal to 1. So 1/2. So we'll say since that 1/2 is less than or equal to 1, the series diverges. Since it fell into this category. So all those that I did before with the integral test, you didn't have to use the integral test. You could have used the p-series test. But at least we see now that you could have used the integral test. Okay, last page. So before we finish up, there's some things that I just wanted to point out. These tests can be very, very helpful, but they can be very specific. All right? So, for instance, 1 over 2 to the n, geometric series. Okay? So you can use the geometric series test. However, if I put an n on the top, it's no longer geometric. 1 over n cubed, that's a nice easy p-series. But look, as soon as I add a little plus 1, no longer a p-series. This series, if I look at its related function of x over x squared plus 3 quantity squared, that one's easily integrated. This one's not so much. So they are, very specific cases on this sheet. So you want to make absolutely sure that whatever series you have fits that form perfectly. If not, then you can't use it. We will see other tests. For instance, this one we would be using a comparison test, likely with, to compare it to this one. But you want to make absolutely sure that you're using the correct test. So, all right, so that finishes section 9.3.